Hello, this is Acid Base 104, Part 2, and these are examples with bases, example calculations, and some examples of equilibrium equations that you'll run into with bases. So I want to start with just the fact that bases increase the concentration of hydroxide in water solutions, and that can happen by either bringing the hydroxide with it or reacting with the water to make hydroxide. And the second point that we want to lead with here is that weak bases have an equilibrium in water. The generalized equation is a base plus water makes hydroxide and the protonated base. And a specific example is ammonia, which is a weak base. So NH3 reacts with water. One of the hydrogens from the water transfers to the NH3 and produces NH4 plus and hydroxide. So NH4 plus is an example of a protonated base. Okay, the other thing we want to remember is that since there is an equilibrium, there is an equilibrium constant. And the equilibrium constant for bases is called KB. And those are in Table 2 in Appendix D. So that's on the back side of the handout that looks like this. There's Appendix D, and it's on the back side. Right here is what I'm talking about. Okay. And the equilibrium constant expression or the KB expression for this equation right here is going to be KB equals the concentration of the hydroxide over the concentration, or times the concentration of the protonated base over the concentration of the base. And that's going to be equal to your KB value. And we want to remember that larger KB values means a stronger weak base. So that means that it takes hydrogens more readily from water than maybe a weaker weak base. So if we look here, I'm gonna zoom in so you guys can see this. If we look on here, we can see that ammonia has a KB of 1.8 times 10 to the minus 5. And aniline, which is related to it, is 4.3 times 10 to the minus 10. So if we're asked which one of these is a stronger base, we would choose ammonia because it has a larger KB. Okay, so we're going to do a couple of example calculations. So here's example 1. We're asked to calculate the pH of a solution that is, we'll say 0.175 molar in, what should we use? How about methylamine? Okay, so we want to, oops, I forgot to scoot out. Okay, there we go. So we're calculating the pH of a solution that's 0.175 molar in methylamine. And what we're going to do is, of course, write an equilibrium equation for methylamine and water. So we write a reaction first for the equilibrium. Methylamine you would find on your little deal here, right here, CH3NH2. And that's aqueous, and that's going to react with water, liquid, and that'll be in equilibrium. Now, when you add hydrogen to these bases that are really big, You want to find the nitrogen and the hydrogens that are attached to it, and you add the hydrogen to these hydrogens here that are attached to the nitrogen. So you would still have CH3, and then you'd have NH3 plus. Because you're adding a hydrogen here, that would be aqueous, and then you would also have hydroxide aqueous. So we're just taking a hydrogen from the water and putting it here. Okay, so that's our reaction. And then of course we're gonna use an ice table. And our initial concentration is given at 0.175 molar. And we don't care about water. These guys are both gonna be 0. We're gonna lose X. So this is just like a weak base calculation. We're gonna gain X. And then our next step is to estimate X out. Because the KB is small. And the KB for methylamine is 4.4 times 10 to the minus 4. So we can say that our KB expression is going to be our protonated base concentration, CH3 NH3 plus, times the hydroxide concentration over the concentration of the original base, CH3 NH2. Okay, so we're just going to substitute our x's here. So we're going to get x times x over, and we're estimating x out. So this is still going to be 0.175, and that's going to be equal to our KB, which is 4.4 times 10 to the minus 4. Okay, so I'm going to do a little bit of baby algebra here. Oops. 4.4 second e negative 4 times 0.175 equals, and then square root. Okay, so we get x equals 0.00877 molar. And want to remember that that represents our hydroxide concentration. So if we negative log x, we're going to be equal to the POH. So negative log of 0.00877 is going to be equal to the POH, which is equal to 2.06. And then if I take 14 and subtract that, I'm going to get 11.94 for our pH. So this is a very basic solution. Because the pH is above 7. Okay. So I think that's it for this example. I'll do a couple more examples in part 3. Thank you.